If a civilization grew so vast, so hungry for energy, that it decided to cage its own sun, what would that look like from here? Could we see it? And if we could, what would it tell us about the universe and about ourselves? You flip on a simple 100-watt lamp without thinking. It feels like nothing. Now picture a civilization so advanced, so desperate for power, it tries to catch every single ray from its star. Not just a bigger lamp, a star in a box. From light years away, that boxed star would play a trick on our eyes. It could look dim or even vanish completely in the light our eyes can see. But it would glow like a warm room in the infrared, which is just a wavelength of light we feel as heat. This idea isn't just science fiction. The physicist Freeman Dyson proposed it seriously in 1960. He was inspired by a 1937 novel called Star Maker. Dyson didn't hand out blueprints for a megastructure. He gave us something more powerful, a search image. Start with that one bulb in your home. Now scale up. The sun puts out about 3.8 times 10 to the 26th watts. That is a number so vast it's impossible to feel. So here is an anchor. Earth, our entire world, catches only a tiny, fleeting slice of that energy. At the top of our atmosphere, we receive about 1.7 times 10 to the 17th watts. Our whole global civilization currently runs on around 20 trillion watts. That sounds enormous, but next to the full power of the sun, it is less than a crumb from a king's feast. In the 1960s, the astronomer Nikolai Kardashev put a label on this dream of scaling up. A Type 2 civilization is one that has mastered its star, harnessing nearly all its power. They eat the whole loaf, not just the crumbs. So what would this stellar engine look like? A giant solid sphere? No. A rigid shell would be gravitationally unstable. It would be torn apart by the very star it was meant to contain. No known material could withstand those forces at that scale. Dyson never meant a single shell. The workable picture is a Dyson swarm. Imagine countless individual mirrors, habitats, and solar collectors, each in its own independent orbit. Together, they move like a vast, slow murmuration of birds around the star. But even a cloud of collectors has a staggering price. To build a swarm around our own sun, just 1 millimeter thick, would require the raw material of several entire planets. Imagine disassembling Mercury, grinding it down into dust in panels, just to begin the project. Each piece of this swarm sips sunlight, then communicates with its neighbors by laser. Each one uses power to live, think, or build. And each one, according to the laws of physics, must radiate away its waste heat. Like every machine you own, but on a cosmic scale. When you burn energy, you have to leak heat. If that civilization lives at a comfortable temperature, say around 300 Kelvin, its waste heat will glow brightest near a wavelength of 10 micrometers. That sits squarely in the mid-infrared. Our eyes cannot see it, but our heat-sensing telescopes can. To us, a caged sun would look oddly faint in visible light. The brilliant shimmer we expect from a star would be gone, but in the mid-infrared, it would shine like a small furnace against the cold of space. This is Dyson's search image, an infrared shadow. Dark where a star should blaze, warm where space should be empty and cold. Dyson made this call to action in 1960. In the journal Science, he wrote that we should search for artificial stellar sources of infrared radiation. For the first time, we had a clue for what an alien intelligence might actually look like. The first tool that could really try came in 1983. A satellite called IRAS mapped the entire sky in the infrared. Later missions like Akari from Japan and NASA's WISE telescope sharpened that image, letting us sweep the heavens for warm things that don't match any known kind of star. In 2009, Richard Carrigan dug through that old IRAS catalog. He hunted for objects that were bright in the mid-infrared, but faint in visible light, a first trawl for Dyson-like candidates. Some objects look promising at first, but with better data, they all turned out to be dusty stars or distant galaxies. Nature, it seems, loves to build things that look like our machines. Could we spot a caged sun here in our own galaxy? The WISE telescope has a band at 22 micrometers, perfectly suited to pick up the glow of room temperature waste heat across much of the Milky Way. But there is a catch. Our galaxy is full of cosmic dust that also glows in the infrared. Sorting the signal from the noise is hard. Still, a swarm that captures most of a sun and runs warm would be hard to miss. A 90% complete swarm radiating at 300 Kelvin would be nearly invisible in an ordinary telescope. But in the mid-infrared, its warm glow would pop out against the background. That is exactly where our best surveys stare. But what if they run colder? The colder a civilization runs, the stealthier it becomes. If you radiate your waste heat at lower temperatures, each square meter of your structure glows more faintly. The same amount of power gets smeared over a larger, colder area, its peak light shifting to longer wavelengths, into the far infrared. In 2015, the Internet's favorite oddball star showed up in data from the Kepler Space Telescope. Its catalog name is KIC 8462852, but most people call it Boyajian star. Its light dipped by as much as 22%, far too much for a planet. And the dips were jagged, chaotic, refusing to repeat on any kind of schedule. Headlines immediately shouted about alien megastructures, but follow-up work cooled that theory down. The star faded more in blue light than in red. That is the classic signature of fine dust. It blocks shorter wavelengths more easily. Subsequent observations pointed not to alien panels, but to a vast, irregular cloud of dust. Nature, once again, with a flair for drama. So we zoom out. What about a whole galaxy of swarms? That's type 3 on Kardashev's scale. A civilization so advanced that most of the starlight in its home galaxy is captured, used, and re-radiated as waste heat. In the mid-2010s, a search led by Jason Wright used the WISE telescope to test this very idea. They scanned millions of galaxies, looking for any that seemed to be missing their starlight, and instead gave off a smooth, uniform surplus of mid-infrared heat. A telltale ember where a bonfire of stars should be. They found none. No clear case where the bulk of a galaxy's starlight had been reprocessed into waste heat. If such galactic empires exist, they are exceedingly rare. Or they run so cold that they are invisible to us. Or, perhaps, they hide very well. False alarms are the rule in this hunt. Nature is a master of disguise. Old, dying stars can cloak themselves in warm dust. Newborn star systems are wrapped in thick, glowing blankets where planets are forming. Entire galaxies can be so drenched in dust, they blaze with the heat of stellar nurseries. All of these natural wonders mimic the very signal we're looking for. And there's another hard truth. We've been looking for civilizations that run warm, like a comfortable room. But what if they run cold? If the waste heat is just a few degrees above absolute zero, its glow slides into the far infrared. Down there, our own galaxy is a bright, lumpy fog. It's like searching for a single candle in a forest fire. Our maps of that cold frontier are still patchy. And so, the score so far is simple: 0. Every promising candidate, every strange warm spot in the dark, has eventually resolved into a natural source as our telescopes got sharper. The hunt continues, but the sky remains stubbornly silent in this particular language of heat. So where would a real one hide? Maybe around the most common stars of all, red dwarfs. They are small, dim, and live for trillions of years. A partial swarm would be easier to build around a small star. It would also be far harder for us to tell apart from a simple, natural dust disk. Even an incomplete swarm can leave strange marks. Odd, non-repeating dips in a star's light. A slow, steady dimming over many years. Mid-infrared colors that almost fit nature, but not quite. New infrared maps of the sky keep sharpening the picture, making the haystack ever smaller for any needle that might be there. The deepest question is not about the hardware, it's about the choice. If physics allows a mind to turn a sun into thought, then today's quiet sky is sending us a message. Maybe the climb to Type 2 is rare. Maybe it is brief. Or maybe civilizations learn that infinite growth is a trap, and they choose efficiency over expansion, going cold and quiet to survive. The absence of embers is a clue of its own. Closer to home, we live on the crumbs of a star. Those crumbs have powered everything we are. But somewhere in the dark, someone could be dining on the whole feast. And if they are, they will leave a warm fingerprint on the night. Until we see it, we keep looking. Thanks for spending your time out here with Stardraft. If this sparked your curiosity, subscribe for more explorations of the cosmos. Take care and see you in the next night.